Welcome to AI Frontiers, a podcast dedicated to exploring the cutting edge of machine learning research. In today's episode, we'll be examining the evolution of machine learning, synthesizing key research trends from 5 papers. This comprehensive analysis covers groundbreaking developments that are shaping the future of artificial intelligence and computational learning systems. Our goal is to provide you with clear insights into where the field stands today and the trajectories that will define tomorrow's innovations. We'll break down complex technical concepts while maintaining the depth and rigor that these important advances deserve. Let's begin our exploration of the rapidly evolving machine learning landscape. Our presentation today covers several key areas at the forefront of machine learning research. We'll start by examining the dominant research themes that are currently shaping modern machine learning, from computational efficiency to multimodal integration. Next, we'll analyze breakthrough methodologies being applied across various subfields, highlighting innovative approaches that researchers are using to solve complex problems. We'll then spotlight groundbreaking results with field-wide impact, focusing on discoveries that could fundamentally change how machine learning systems are designed and implemented. The presentation will also identify emerging trends and future research directions, giving you insight into where the field is headed. Throughout, we'll synthesize insights from seminal papers that exemplify the current state of machine learning research, providing a comprehensive view of the field's evolution. Before diving into specific research themes, let's establish a broad understanding of the machine learning landscape. Machine learning encompasses algorithms that enable computers to learn patterns from data without explicit programming instructions. The field has evolved dramatically from early rule-based systems to today's sophisticated deep learning and transformer architectures. This evolution has been powered by 3 key factors: the explosion of available data across domains, significant advances in computing hardware including specialized processors, and continuous algorithmic innovation that has enabled more efficient and effective learning. Machine learning applications now span numerous domains including recommendation systems that personalize content, natural language processing that powers conversational interfaces, computer vision enabling automated image analysis, and critical decision support in healthcare and finance. Recent years have seen growing emphasis on making these systems more efficient, interpretable, and aligned with human values, addressing both technical limitations and ethical concerns. Our analysis reveals several dominant research themes, the first being computational efficiency. As models grow larger and more powerful, researchers are focusing intensely on making them more computationally accessible. In groundbreaking work, Camille and colleagues demonstrate fully quantized training with 4-bit precision for weights, activations, and gradients, a significant reduction from the standard 16 or 32-bit precision typically used. Other researchers have developed communication-efficient frameworks that accelerate transformer inference through innovative sequence parallelism techniques. These approaches achieve significant speedups in bandwidth-constrained environments, addressing a critical bottleneck in deploying large models. Importantly, these efficiency improvements maintain comparable downstream performance despite the reduced precision. This research theme directly addresses the growing tension between model capability and resource requirements, making advanced AI more accessible and environmentally sustainable. The ability to train and deploy powerful models with substantially lower computational resources represents a critical advancement for both research and practical applications. The second major research theme focuses on advances in reinforcement learning, with particular emphasis on simplifying complex algorithms. Several papers challenge conventional wisdom about trust region enforcement in policy optimization. Researchers demonstrate that vanilla policy gradient methods can match or even exceed the performance of more sophisticated algorithms like proximal policy optimization, PPO, simply by increasing the number of value update steps per iteration. This finding suggests that enhanced value estimation accuracy, rather than trust region enforcement, may be the critical factor driving performance in these methods. Other researchers introduce decision transformer models that enable zero-shot generalization to new scenarios without retraining, encoding goals and constraints directly as prompt tokens. These developments reflect a broader trend towards simpler yet more effective approaches to long-standing challenges in reinforcement learning. By identifying which components truly drive performance, Researchers are creating more robust and computationally efficient algorithms that maintain or improve upon state-of-the-art results. The third significant research theme centers on AI alignment and interpretability, ensuring that systems reflect human values and can be understood by their users. Researchers are developing theoretically grounded approaches for efficient collection of human preference data, explicitly accounting for the influence of the language model being aligned when selecting training examples. Contrastive learning frameworks are being applied to address the alignment tax problem, where Debayesian approaches often degrade model capabilities. These methods balance bias mitigation with faithfulness preservation, demonstrating improvements in both toxicity reduction and knowledge retention. On the interpretability front, local data attribution frameworks now trace model behavior back to individual training samples, enabling diagnosis of learning processes, analysis of behavior formation, and targeted intervention during training. Interpretable multimodal interaction-aware frameworks enhance modality fusion while providing interpretation at both local and global levels. These developments reflect growing recognition that black box models, despite impressive performance, face adoption barriers in critical applications where understanding decision processes is essential. The fourth research theme explores multimodal integration, breaking down data silos between different types of information. Researchers have developed efficient language-image pre-training frameworks that amortize expensive computations involved in contrastive learning through lightweight neural networks. These approaches improve training efficiency and performance in text-image tasks. Novel methodologies now enable models to think with images during reasoning processes, interleaving text and visual reasoning steps in multimodal chains of thought. This represents a significant advance over previous approaches that produced text-only reasoning conditioned on static image inputs. Hybrid attention architectures specifically designed for human activity recognition using wearable sensors combine transformer-based temporal modeling with channel-wise attention mechanisms to capture activity-specific motion dynamics. These multimodal integration techniques aim to mimic the human ability to process and synthesize information from multiple sensory inputs, enabling more natural and powerful AI systems that can seamlessly work across different data types and representations. Across the papers analyzed, several breakthrough results stand out for their potential to reshape machine learning research and applications. Camille and colleagues demonstrate that 4-bit precision is viable for the entire large language model training process, successfully training a 7 billion parameter model while maintaining performance comparable to higher precision baselines. This addresses one of the field's most significant barriers to large-scale AI development. Another key finding challenges fundamental assumptions about reinforcement learning, showing that value estimation accuracy, not trust region enforcement, drives policy gradient performance. This insight enables simpler algorithms to achieve state-of-the-art results with better hyperparameter robustness. In multimodal learning, researchers have developed the first frameworks enabling true visual reasoning in vision language models through multimodal chains of thought. On the theoretical front, work on Langevin dynamics shows that generalization is bounded by temperature, independent of dimensionality. A surprisingly simple yet powerful result. Finally, domain-specific benchmarks and models for fields like agriculture demonstrate how targeted datasets can unlock specialized reasoning abilities in language models, expanding AI's practical impact. Several methodological approaches appear consistently across the papers, reflecting current best practices in machine learning research. Reinforcement learning from human feedback, RLHF, has emerged as a powerful methodology for aligning AI systems with human preferences and values. This approach involves collecting human preference data, training a reward model based on these preferences, and optimizing policies to maximize the learned reward function. Mixture of experts, MO, architectures enable scaling model capacity while controlling computational costs by activating only relevant sub-networks for each input. Quantization techniques reduce numerical precision while maintaining performance, significantly decreasing memory and computation requirements. Neural operators learn mappings between function spaces for modeling physical systems, enabling generalization across different discretizations and initial conditions. Contrastive learning enables self-supervised representation learning by bringing similar examples closer in representation space while pushing dissimilar ones apart. These methodological approaches represent the current state of the art in addressing key challenges across different machine learning domains. Let's examine one of the most significant papers in detail. FP4 All the Way. Fully Quantized Training of Large Language Models by Camille and colleagues. This work represents the first demonstration of fully quantized large language model training using 4-bit precision throughout the entire training process, for weights, activations, and gradients. Previous approaches typically maintained higher precision for certain operations or model components, but this work shows comprehensive 4-bit training is viable. The researchers conducted a systematic investigation of key design choices including block sizes, scaling formats, and rounding methods to identify optimal configurations. They successfully trained a 7 billion parameter model on 256 accelerators, achieving downstream task performance comparable to standard higher precision baselines. This breakthrough addresses a critical barrier to large-scale AI development: the enormous computational resources typically required for training. By demonstrating that 4-bit precision maintains model quality while drastically reducing computational requirements, this research opens the door to more efficient, accessible, and environmentally sustainable AI development, potentially democratizing access to advanced language models. Another seminal paper challenges fundamental assumptions about reinforcement learning algorithms in Challenging Trust Region Enforcement in Policy Gradient Methods. This research questions the widely held belief that enforcing approximate trust regions leads to steady policy improvement in reinforcement learning. Through careful experimentation, the authors demonstrate that the more critical factor in the success of modern policy gradient algorithms like trust region policy optimization and proximal policy optimization is actually the enhanced value estimation accuracy from additional value update steps in each iteration. The methodology involves a simple but powerful modification: increasing the number of value update steps per iteration. With this change, vanilla policy gradient methods achieve performance comparable to or better than more complex algorithms across standard continuous control benchmark environments. This finding has significant implications for algorithm design and hyperparameter robustness, suggesting that reinforcement learning algorithms may be made more effective through simpler modifications than previously thought. The work challenges researchers to reconsider fundamental assumptions about what drives performance in policy gradient methods. The third paper we'll highlight introduces groundbreaking capabilities in multimodal AI, training vision language models to generate multimodal chains of thought. This research presents the first framework that enables vision language models to generate true multimodal reasoning chains by interleaving text and intermediate visual reasoning steps. While previous approaches to extending reinforcement learning fine-tuning to vision language models largely produced text-only reasoning conditioned on static image inputs, this new approach enables genuine multimodal reasoning in the response. The methodology integrates visual editing tools into the reinforcement learning fine-tuning process, allowing models to learn when and how to generate visual reasoning steps that benefit final reasoning. The training process uses outcome-based rewards tied to task accuracy rather than process-based supervision, eliciting strategic visual tool use without prescribing exactly how the tools should be used. This breakthrough addresses a fundamental limitation in current vision language models: their inability to think visually during reasoning processes. By enabling models to generate and manipulate visual representations as part of their reasoning chain, this approach opens new possibilities for more sophisticated multimodal AI systems. Looking toward the future, several emerging frontiers in machine learning research deserve attention. Ultra-efficient training and inference through novel quantization techniques will likely continue to advance, potentially enabling even larger models to be trained with limited resources or bringing powerful AI to edge devices. We can expect further development of simplified yet more robust reinforcement learning algorithms that maintain performance while reducing complexity and improving stability. Multimodal reasoning that truly integrates different modalities in thinking processes represents a particularly exciting frontier, moving beyond treating different data types as separate inputs toward genuine multimodal cognition. Domain-specific AI systems for underserved fields like agriculture, materials science, and climate modeling will expand AI's practical impact to crucial real-world problems. Finally, alignment techniques that preserve model capabilities while ensuring safety and ethical behavior will become increasingly important as AI systems grow more powerful and widely deployed. These frontiers collectively point toward AI systems that are more capable, efficient, trustworthy, and broadly applicable across domains. This synthesis was created using a combination of advanced AI systems, including GPT and Anthropic's Claude 3-7 Sonnet 20,250,219. The text-to-speech synthesis you're hearing was performed using Google's TTS technology, while visual elements in the accompanying presentation were generated using OpenAI's image generation capabilities. All content underwent review by a human expert for accuracy and coherence before publication. While we've made every effort to provide a comprehensive overview of current machine learning research, some oversights may exist due to the vast scope of the field. All references to original research papers are provided in the show notes to enable further exploration. This synthesis represents our best understanding of the current state of machine learning research based on the papers analyzed, but the field continues to evolve rapidly, with new breakthroughs emerging regularly. We encourage listeners to consult the original research papers for the most detailed and authoritative information on specific topics. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from the archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Subscribe to our YouTube channel for weekly research breakdowns featuring comprehensive coverage of cutting-edge AI and ML developments. Our expert analysis of emerging trends and breakthrough papers provides accessible explanations of complex technical concepts. Join our growing community of researchers, practitioners, and AI enthusiasts to stay at the forefront of technological innovation. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archive.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archive.org.